Hey everyone, welcome to our fourth week of online lectures, and we're going to skip to Chapter 7. And Chapter 7's got a couple of things I want to touch base on. One is how chemical reactions occur, and how quickly do they occur. That's chemical kinetics. And we'll also talk about equilibrium and heat. And this will be kind of a very short run through of this chapter, so we won't spend too much time on here. But the question is, how does a reaction occur? And a generic reaction might be a couple of reactants, A and B, and they somehow change into C and D. And so far in this class, we've only really just considered ourselves with, if you know how much A you have, how much B do you need, and how much C and D do you make, those kind of questions. But now we're going to go ahead and ask the question, how does this reaction actually take place? And the model actually looks something like this. So we're going to imagine that the reactants have to bump into each other. So we start with A and B, and for a brief instant in time they are moving towards each other, and we're going to go ahead and we're going to take time on this axis down here. So imagine this is like a movie strip, if you remember movies. So A gets closer and B gets closer, right? So they're moving towards each other, and then they actually bump into each other, and so A and B now, right, are touching each other. And this is where something has to happen, and it turns out there are two futures here. So future one, which I'll draw in red, and I'll go off to the left here, says that A and B basically just bounce into each other, and then they bounce off of each other. And most of the time, actually, this is all that happens. The reactants actually just bump in and bump right back off of each other like a couple of snooker balls, let's say. But every now and again, you see something really weird, right? So to the left here is a no reaction. So nothing is happening here at all. They're just bouncing off of each other. But every now and again, what happens is that the reactants actually merge with each other. So they actually mesh together here. So I've drawn them kind of smushing into each other. And when they smush into each other, they actually start to change. So they start to form what we call a transition state. I'll write TS for short here. And this is sort of this point where the atoms are starting to swap between each other. So if A and B are big groups, maybe there's a hydrogen that has to swap from one to the other. And so imagine two things smashing into each other so hard they actually trade bits of each other. And then this transition state actually breaks down, and when it breaks down, it actually has the products C and D, and then they just sort of move away from each other. So we've got these two possible paths here. So we've got the one path where they basically just bump into each other and bump off. And then we've got the other path, the interesting path, where they bump into each other so violently they actually swap atoms. They move through this transition state, right, where they're actually kind of plopping one atom onto the other, and then the reactants basically just fall apart in the next step. What you find is that 99.999% of the time the atoms just bump into each other and bump right back off. But every now and again, like one time in a billion, they actually collide so hard, bits of the one molecule kind of trade places with bits of the other, and they form a reaction that forms the product C and D. We can draw a graph that shows what's going on here. I'm going to draw a vertical axis here, and this is going to be energy. And a horizontal axis, you can think of this as time maybe, or extent of reaction. So over on the left, you basically haven't had a reaction yet, and on the right, you have had a reaction. And I'm going to go ahead and draw this graph in blue. So initially, you've got your reactants A and B, and they are bumping into each other. And as they bump into each other, just like two balloons being forced together, they kind of squish and repel, and the energy goes dramatically up. Kind of like a spring where you're just pushing hard on it, and you got to put all that energy in. And what you find is that you push them so hard, they actually start to swap atoms now, and so little bits of A fall onto B or vice versa. They move through that transition state, right? And then as the atoms move and form the products, they go back down in energy again, and the curve looks something like so. And all the way on the right hand side, you've got our products. So we can imagine, if you like, our molecules are bumping into each other here, and as they bump into each other, they rise in energy, and if we squeeze them together so hard, they need an awful lot of energy. All of a sudden, they move through this transition state, this point of no return, and then they just kind of fall down the energy diagram and form products, something like that. In fact, it's probably more proper to, instead of write energy, to write potential energy, because potential energy is energy that depends on position. And so this energy here depends on how far apart the atoms are from one another. So when they're really, really close to each other, right, they have a lot more energy than when they're really far apart. So right here, they're pretty far apart, and as they move through the transition state, they're very close together, and then they pull apart and form products so that their energy goes right back down again. I think a really nice analogy here is, imagine this is sort of a cross-section of a hill, and you are standing where the reactants are down here, and these are the days when you can go outside and play. So what you're going to do is you're going to play a game, and you're going to throw this ball, and this ball is going to throw out of your hands, right, and it's going to roll up the hill, and of course it can get to a certain position, and then it stops and it rolls right back. And depending on how hard you throw the ball, depends on how high it can go. So if you throw it a little bit, it goes up and then stops and then rolls back down to your feet. And if you throw it a little bit harder, it can go a little bit further up, and then it stops and then it rolls back again. And if you throw it really hard, you can throw it so that it rolls all the way to the tippy top and then just stops right here. So you give it a certain amount of energy, it can reach this transition state, and a little gust of wind can kind of take it off to the other side, and it just rolls back down to the product side of the equation. And if you throw it harder than that, then it can go on up and whiz through the transition state and go and form products. So you can think of this as an analogy to our reaction here. There's a minimum energy then that you have to throw the ball with, and this is called the activation energy. And I can draw a line from the bottom of the reactants to the top of the transition state, and I can measure this energy here. This is called the activation energy, or E with a little subscript A for short. So let's go ahead and write that down. So activation energy, and this is the minimum kinetic energy, so the energy of motion, so the minimum kinetic energy that the reactants have to hit with in direction. The molecules are constantly bouncing off of each other, and just like we said for gases, their energy depends on the temperature, so the reactants there, depending on how hot or cold they are, if they're hotter, they're bumping into each other more violently. If they're colder, they're sort of more gentle about it. But the reactants have to bump into each other with an energy that is bigger than this activation energy, and then they can go to the other side. You can think of this as a cover to a club, and so maybe the club charges a $50 cover, and if you come in with $20, you can't enter. If you come in with $49, you can't enter, presumably. If you have $50, you can enter, but you can't buy any pop on the inside. And of course, if you have more than $50, you can come in and keep the change. So this activation energy is the minimum energy we've got to pay in order for the reactions to complete and form products. So how does the activation energy affect the reaction rate? So we can go ahead and we can draw our diagrams again. So this is potential energy, this is reaction coordinate or time, and we said the activation energy, right, is that barrier height. So you can think of that as the cover the nightclub needs you to come in and supply before you can come in. So this is a high activation energy barrier, and maybe we've got another reaction with a low activation energy barrier. So it's got a much smaller the difference there in energy between the reactants and the transition state. So here we go. So this is exactly the same reaction, if you like, just the only difference is the barrier height. So on the right hand one, it's kind of small. And how would this affect the reaction? Well, think of this as, how would this affect the ball you throw over the hill? If the hill is really steep, you got to throw it extremely hard before it can roll over. But if the height of the hill is very small, it's really easy to roll it over to the other side. So think the difference between rolling a ball over Mount Everest and rolling the ball over a molehill. So it's much easier to go over a molehill because it's a much lower energy to defeat. So in general, we find that the smaller the activation energy, the faster the reaction. So just think the smaller the cover to the nightclub, the more people can go in. If it's $1 million cover, right, you and I and probably everyone else in the class is not going to be able to afford it. So reactions that have a low activation energy are very, very fast.